Good day everyone, we are the Group 8 and today we will be presenting our report on camera. Cameras have become an essential part of our daily lives, from capturing memories to advancing scientific discoveries. But have you ever wondered how these devices truly works, or how it all began? So in this report, we'll take you on a journey through evolution of cameras, from the simple pinhole models of the past to the high-tech digital cameras we use today. At the end of the lesson, the students will be able to explain the evolution and purpose of cameras from pinhole to digital types, describe the basic optical principles and components that make a camera work, and relate camera functions to the physics of light and image formation. Good day everyone. Now, let's start with a very simple yet fascinating question. What exactly is a camera? So today I'm going to introduce to you what is camera and its purpose and evolution. So let's begin with its purpose. So a camera is a device that captures and records light to create images, whether still photos or moving videos. So imagine it is an artificial eye. It sees through a lens, focuses light and captures a moment that would otherwise fade away. So the word camera actually comes from the Latin phrase camera obscura, which means dark chamber. In early times, artists used this concept to trace outline of scenes projected through a small hole in a dark box. That's how the idea of photography began. So today's cameras, from professional DSLRs to the tiny ones in our smartphones, still follow the same principle. They just use digital sensors instead of film and advanced electronics to store, process, and enhance image. So yeah, the basic concept remains unchanged since the earliest camera obscura to capture and preserve moments visually. So modern cameras integrate optics, electronics, and software for image capture and processing. So in short, a camera's purpose is to capture reality through light, a blend of art, science, and technology working together. Now that we know what camera is, let's travel back in time and explore how it evolved. So it all started with a pinhole camera or the camera obscura around the year 1000 AD. The scientist Ibn al-Haytham, also known as Alhazen, was the first to study how light passes through a small hole to form an inverted image inside a dark room. And fast forward to 1826, Joseph Nicephore Niepce created the world's first permanent photograph. It took 8 hours to expose one image. So imagine waiting that long for a single photo. Then came George Eastman's Kodak in the late 1800s, which made photography accessible to everyone. So cameras became portable and user-friendly. And in the 20th century, film dominated from black and white color and even instant photos from Polaroid. Finally, in the digital era, starting in the 1970s, engineers developed CCD sensors, replacing film with pixels. These paved the way for digital cameras, DSLRs, and the high-resolution smartphones cameras we use today. So from boxes with holes to pocket-sized wonders powered by artificial intelligence, cameras have evolved remarkably. Yet their core idea remains the same: capturing light to tell a story. Now let's dive into the science behind how cameras actually work, and the physics of optics and light. So every photo starts with light. So light travels in straight lines and bounces off objects into the camera lens. The lens then bends or refracts the light to focus it onto a surface, either film or a digital sensor. So the aperture, which acts like the eye's pupil, controls how much light enters. So a wide aperture lets in more light and gives a blurred background, while a narrow aperture increases sharpness. So the shutter controls how long light hits the sensor. Fast shutter speeds freeze motion, while slow ones capture movement or light trails. So this process is pure physics. The way light bends, focuses, and interacts with the lens follows the same principles taught in optics. In fact, the human eye and a camera share the same working idea. A lens focuses light onto a sensitive surface, forming an image our brains or processors interpret. So when you take a selfie, remember, you're actually applying the laws of light and physics.
So, now let's proceed to the basic optical principles of camera. So I believe all of us uses camera in our daily life to take pictures of the places you've been to, persons you like, things, events, or whatever it is for whatever reason. Even now we're using camera to take videos of our reporting, no? So it is not new to us anymore. So it has various principles, but let's focus on refraction, focus on focal length. So let's first talk about refraction. So refraction is the bending of light when it passes from one material to another, like from air into the glass lens of camera. So this bending happens because light travels at a different speeds in different materials. So in a camera, the curved lens bends the light rays so they meet at a single point, that is the focal length, no, or focal point on the image sensor. So that's how clear image is formed. So kung wala ni si refraction, the camera won't be able to direct light properly and the photo would turn out to be blurry or distorted. Next is focus and focal length. So every lens has a focal length. So focal length, this is the distance from the lens to the point where the light rays converge when the subject is far away. So to focus on objects at different distances, the camera moves the lens elements closer to or farther from the sensor to ensure the image is sharp. So short focal length, this is the wide angle view, and then the long focal length, this is the magnified or zoomed in view. To explain it further, let's first talk about focus. So focus, this is what makes sure that the image is sharp and clear. So to do this, if you're using your phone's camera, all you have to do is to click or tap the subject that you want to focus on. Pag mag-focus na tayo na siya, so you can take a picture then. Next is, if you're using a camera, all you have to do is to adjust the lens or adjust the position of the lens so that the light rays from the subject meet exactly on the image sensor. So if the lens is too close or too far, the image becomes blurry. So dapat adjustment gid ka. So most modern cameras have autofocus systems that do this automatically. Pero napayuban nag-allow Japon og manual focus. So depende lang gid na siya sa camera. So next is the focal length. So again, what is focal length? Focal length is the distance between the lens and the point where the light rays come together to form an image. So focal length affects how much of the scene the camera can capture. So we have the short focal length, which gives you the wide angle view. So kanisa ang mas kanang gamiton pag imong ginapicturean is landscape or group shot or group photos. We also have long focal length. This is the zoom in on distant objects. So this is perfect for wildlife or sport photography or basta lang ka na whatever picture that you want to i-zoom in mo so that you can have a clear photo of that. So, by changing the focal length, we can control how close or how far the subject appears on the photo. Just remember this, no? Si refraction, that is what bends the light to form an image. Focus, this is what makes sure ng imong picture or imong image is sharp and clear. Si focal length is this is what controls how close or how far your subject appears in the photo. So, in other words, this controls how zoomed in or wide the image is.
Good day everyone! Today I'll be talking about camera lenses and image formation. So cameras may seem very modern and advanced, but the way they form images is actually based on simple physics, mainly how light behaves when it passes through lenses. So the most important part of a camera is the convex lens. So this type of lens curves outward and makes light rays come together or converge at some point. So when a light from an object enters the lens, it bends and forms a real and inverted image on the camera's sensor. So this is how cameras are able to produce clear and focused pictures. So concave lenses are also used inside cameras but not to form the main image. Instead, they are used to correct distortions and improve zoom lenses. So next would be the lens formula. So to understand how a lens form an image, we use the lens formula, where 1 over f is equals to 1 over do plus 1 over di, where f is the focal length of the lens, do is the distance from the object to the lens, di is the distance from the image to the lens. So, sample problem. For example, if a lens has a focal length of 50 millimeters and the object is 2 meters or 2000 millimeters away, we can calculate the image distance using this equation. So, we have our givens, focal length is equals to 50 millimeters and object distance, which is equals to 2000 millimeters. So, we're going to substitute the given to our formula, and then we will calculate that to get 39 over 2000, or di would be equivalent to 51.28 millimeters. Next would be the magnification of the image. So magnification tells us how big or small the image appears to the real object. So the formula is m is equals to hi over ho, or could be di over do, where hi is the image height and the ho is the object height. So we have our simple sample problem. If a person is 1.8 meters tall, or that is also equivalent to 1,800 millimeters, and we use di equals to 51.28 millimeters and do would be equal to 2,000 millimeters, then we are going to substitute the given values. So the distance from the image di equals 51.28 would be substitute to the formula. So 51.28 divided by 2,000, we will get 0.256. Next is we're going to discuss the aperture and f number, or the brightness of an image. So the aperture is the adjustable opening of the lens that lets light into the camera. So the brightness is measured using the f number. So the size of this opening affects the brightness of an image. So the brightness of an image is determined by the f number. F number would be equal to f divided by d, where f is the focal length and d is the diameter of the lens of the opening. So for example, if f is equals to 50 millimeters and the aperture diameter is d, which is equals to 25 millimeters, then 50 divided by, substitute the given, 50 divided by 25 would be equal to 2, or also written as f divided by 2. So a smaller f number means a brighter image and a blurrier background. So next is the depth of field and lens aberration. So the depth of field refers to how much of the photo appears sharp and in focus. So a large depth of field means that both the foreground and background are clear. A shallow depth of field means only the subject is sharp while the background is blurred. So lens aberration are imperfection in lenses that cause distortion or blurriness in image. So, a sample problem. So, an object is 5 meters or 5,000 millimeters away and the image forms 50 millimeters behind the lens. So, find the focal length using the formula. So, we have our given 5 meters. An object is 5 meters or 5,000 millimeters away and the image that is formed behind the lens is 50 millimeters. So, we're going to substitute that to our formula. So, 1 divided by 5,000 plus 1 divided by 50, we're going to get 1 divided by f, which is equal to 101 divided by 5,000. That will equivalent to 49.50 millimeters or approximately 50 millimeters. So the camera lens in this problem needs a focal length of approximately 50 millimeters to focus on this object. So in summary, convex lenses are responsible for forming real images on the sensor. Aperture controls brightness, depth of field adjusts focus range, and lens aberration affect image quality. So thank you for listening.
So good day everyone. Today I'll be discussing camera components and exposure. So these two are important concepts in photography because these two determine how a camera captures and produces an image. So first, let's talk about the main components of a camera and to be followed by exposure, which controls the brightness of a photo. A camera is made up to several parts that work together to capture an image. So here are the main components and their function. So the first one is the aperture. So the aperture is the opening in front of the camera. It will be present in the lens part. For an interchangeable lens camera, you will have the option to change the lens. So you will have more options with the aperture. But for a standard point or a shoot or bridge camera, the lens is a fixed one. So the options are very limited. You can only vary the aperture in lens from the camera body. So next is the lens. The lens focuses on the image sensor. The lens primary function is to determine how sharp and clear the image will be. Number 3 is the shutter, which controls the time duration for which the image sensor is exposed to the light. The shutter is one of the vital parts of a camera because from what I've said, it controls the time duration for which the image sensor is exposed to the light. Most digital cameras came with a combination of electronic and mechanical shutter or mechanical alone. All digital cameras are designed for a specific shutter light, which we call the camera shutter count. The reliable shutter operation is guaranteed only up to this value, but those top-end models will come with a higher shutter count. So next is the image sensor. It captures the light and converts it into an electronic image. Also, it is the most important part of a camera. It also decides the image resolution, thus it is like the heart of the camera. In the early days, the film used to this job. Now, it got replaced by CCD or CMOS sensors. They are responsible for acquiring each of the pixels in an image. An image sensor is quantified based on its size and number of megapixels. So next is the viewfinder. This viewfinder is a small rectangular opening which we see on the top of the camera. You can see through this window to compose and frame the shot. Digital cameras either have an optical viewfinder or an electronic viewfinder. So the viewfinder, also known as parameters like exposure, dili na to gakikita ang shutter speed, aperture, and ISO, and a few other basic settings for image capture. So once again, viewfinder is the small rectangular opening which we see on the top of the camera. Next is the light meter. One of also the components of the camera is the light meter, which it measures the brightness of a scene and help adjust exposure settings. The light meter, siya ang measures into our brightness in order for our photo to be much more clearer and being exposed. So next is the inbuilt flash. In digital cameras, there are more than 90% has a inbuilt flash. It is found in the top side. Also, it will pop up only when you enable flash in the settings or you enable the flash manually. So, most of the camera are nanasashay ka ng inbuilt na flash, which pwede nimo siya i-on manually or in the settings. So next is the storage card, or dili ta mag-save to our photo or our videos nga atong na-captured. So lastly is the battery and battery compartment. So most cameras ko, if ever wala battery ang camera sa lugar pag under, no. So most cameras use lightweight rechargeable lithium polymer batteries. It will be a custom one which supplied along with the digital camera. So these are the pictures, the lens. So what comes in the lens is the aperture. In the front view, we see the shutter trigger, the shutter, camera body, and the image sensor. In the back view, we see the viewfinder, the button, interface, the mood dial, the inbuilt flash. We see also the shutter trigger. So some cameras have secondary LCD display. While in the back view, sa third image, we see the primary CD display, the hot shoe, and also at the side view, we see the memory card slot, which primarily function to store the video and the photos. And the last one is in the bottom view, which we see the tripod mount, and the battery compartment. So let's proceed in the camera exposure. So what is exposure? It refers to how much light reaches the camera's image sensor. Also, it determines how bright or dark a photo appears. If too much light enters the photo, it becomes overexposed or too bright. But if it is too little light enters, it becomes underexposed or too dark. So achieving proper exposure is all about balance. Exposure is controlled by three main settings known as the exposure triangle. These are the aperture, the shutter, the speed, and the ISO. So first, what is aperture? Aperture controls the size of the lens opening. So meaning to say, when it has large aperture, it is the small fraction number like f1.8, meaning to say it lets in more light and creates a blurry background. But in small aperture, like large fraction number like f16, it lets less light but keeps more of the image in focus. So next is the shutter speed. Now, I'll be talking about shutter speed. One of the easiest yet most powerful camera settings to understand. Shutter speed, it refers to how long the camera shutter stays open when taking a picture, from 1 to 100 of a second to 30 seconds or more. So what is the shutter speed? It controls how long light reaches the image sensor, and it affects two things, the brightness of the image and the motion blur or sharpness of moving objects. So first, let's go to the effect on the brightness. So once it is long shutter speed, example 5 seconds, more light or brighter photo. While fast shutter speed, example 1 to 800 seconds, less light, darker photo. Using prolonged shutter speed in bright light can cause overexposure. So next is the effects in motion blur or the sharpness of the moving objects. In slow shutter speed, in motion, it captures movement as blur, which it is great for waterfalls or night trails. While in fast shutter speed, freezes motion, which is great for sports or wildlife. So next is the types of motion blur. In motion blur, there are two types, which is the camera blur, which is caused by camera shake. So in order to fix this, use a tripod. Next is the subject blur, caused by movement in the scene. A tripod won't fix this, so because the subject itself is moving. So to summarize, the shutter speed affects light and motion in your photo. Slow shutter speed, meaning more light, more blur. Fast shutter speed, meaning to say less light, frozen action. So balancing shutter speed and aperture and ISO helps you capture sharp, well-lit photos. Next is ISO. When we talk about camera settings, we often hear about aperture, shutter speed, and ISO. But did you know that ISO is not actually part of exposure? ISO doesn't control how much light enters your camera, but it simply brightens your photo digitally. After the sensor captures the light, think of it as your camera's built-in brightness booster. Let's proceed to exposure value, or the EV formula. EV is equals to log2 N2 over T, where EV is equals to the exposure value, while the N is equals to the aperture, and the T is equals to shutter speed. So solving equation, if your settings are f4 and 1 over 125 seconds, first is the formula, then write the value f, which is in the first one. In the N2 is 4.2 over 1 over 125. So why it appears multiplication na yun, which is 4 times 4 is equals to 16 times 125, because it is in the fraction form. So instead of division, convert into multiplication. So 16 times 125 is equals to 2000 log 2. Then the result is 10.97 or 11. So we can see here that the lighting condition is very bright daylight. Okay, naman siya into 11. And that's all. Thank you.
Good day everyone. Today I will be presenting about applications, challenges, and advanced physics and optics. We will explore how optical technology is used in modern devices like smartphones, cameras, telescopes, microscopes, CCTV, and even medical imaging tools. We'll also discuss the limitation caused by physics and the latest technologies that help overcome these challenges. So first, optics is the science of light and how we form images using lenses and sensors. Many devices in our daily lives rely on optics, from photography to scientific research. As technology advances, both physics and software play key roles in improving image quality. So let's start with cameras. Smartphones have small lenses and sensors, so they rely heavily on computational photography, meaning software enhances the picture. On the other hand, DSLR cameras have bigger sensors and lenses, capturing more light naturally. DSLR gives photographers more manual control and deeper image detail. So if we compare them, smartphones are designed for convenience and portability, while DSLRs are designed for professional creativity and image accuracy. The key difference, smartphones enhance photos using AI, while DSLRs depend on superior optical hardware. So in applications in optical devices, optics isn't only for photography. Telescopes allow us to observe stars, and galaxies. Microscopes let us study in tiny organisms and cells. CCTV cameras provide security and surveillance, especially in low light. In medicine, optical tools like endoscopes help doctors see inside the body without surgery. So in common optical problems, however, optics still faces challenges due to the physics of light. Diffraction causes image softening because light behaves like a wave. Lens flare happens when stray light reflects inside the lens. Chromatic aberration creates colored fringes because different wavelengths bend differently. These issues reminds us that optics is limited by nature itself. So in modern optical technologies, to solve these limitations, modern technologies were developed. Autofocus quickly adjusts focus for a sharp image. Optical stabilization reduces shaking during shots. HDR balances bright and dark areas in photos. AI imaging identifies scenes, removes noise, and enhances clarity. Together, these advancements helps cameras produce sharper and more detailed images. So in diffraction limit physics, now let's go deeper into physics, the diffraction limit. This formula shows the smallest detail a lens can resolve. Theta equals 1.22 lambda over d, where lambda is the wavelength of light and d is the lens opening. The bigger the lens aperture, the smaller the diffraction effect, meaning better resolution. So sample calculation. Here's a simple calculation using a camera lens 2 cm wide and green light with a wavelength of 550 nanometers. When we apply the formula, we find the minimum resolvable detail is around 0.168 millimeters at a distance of 5 meters. This shows how camera performance is directly affected by physics. To sum it all, the study of cameras and their optical principles highlights the profound connection between physics and modern technology, from the early pinhole camera to advanced digital and AI-assisted imaging systems. The fundamental laws of light and optics continue to govern how images are formed and captured. Understanding concepts such as reflection, refraction, exposure, and diffraction not only deepens our knowledge of camera function but also demonstrate how physics enables innovation in imaging, communication, and scientific exploration. That's all. Thank you.